Hello once again. This video is all about the idea of mathematical induction. Mathematical induction is a really powerful tool for proving formula. And you'll see a couple of examples of that today. And hopefully you'll be able to use it. So before I do that, I'm going to give you a bit of an analogy. I'd like you to imagine that you've got an infinitely tall ladder. So there's my infinitely tall ladder over here. Infinitely tall. And I want you to be able to climb this ladder. I want you to be able to climb this ladder. Here you are. There you are. Unless you're Niels, in which case there you are, Niels. And I want you to be able to climb this ladder. To climb the ladder, you basically have to have two skills. The two skills you need to be able to climb this ladder are, firstly, you need to be able to get on the bottom. You need to be able to get on the ladder. If you can't get on the ladder, you can't climb it. And the second skill you need to be able to climb this ladder is you need to be able to get from one rung to the next. If you can do those two things, you can get as high as you like on the ladder. You can get to any point you want on this infinite ladder. If you can't do one of those two things, then you can't climb the ladder. So, and that's what mathematical induction is. Mathematical induction is a proof that relies on these two ideas. So, I'm going to be a little bit more explicit. I'm going to give you an example. And hopefully, this will make things clearer. So, I'm going to prove that if you add up the odd numbers, you get a square number. I'm going to prove if you add up the square numbers that you get a square number. Before I even try to prove that, I'm going to write it down in symbols. So an odd number will be given by 2n minus 1. That'll give me the odd numbers. First odd number, 2 times 1 minus 1 is 1. Next odd number, 2 times 2 minus 1 is 3, and so on. So they're the odd numbers, so we're going to add them up. Add them up from 1 to whatever I like. Probably shouldn't be using n because I'm going to use n on the other side. Let's call it r. That's what we've been using. I'm going to add them up to whatever number I like, up to n. And I'm saying that will give me a square number. This is a fact that we already know. It's a fact that we've known for a long time. If you write the square numbers out, then you see it comes by adding 3, adding 5, adding 7, but I don't think we've ever sat down and explicitly proved it. So the proof that we're going to see was first proposed by a guy called Francesco Marolico, who I would imagine, from his name, was Italian. And he is usually credited as the first person to prove anything with mathematical induction, and he did it in the 16th century. That's what his proof looked like. A dense text of Latin. He didn't have the powerful symbols and notation that we have today. So his proof is much more impressive in a way than what I'm going to do. because the invention of algebra, the invention of symbolic algebra in particular, makes this whole process hopefully a lot easier. So how do we go about doing it? Well, we need to prove two things. We need to prove that it's true at the start, so it's true for the first number, and then what we do is we prove that it's true for, if I start at one place, it's true for the next number. So this is similar to our ladder. I'm going to go back to the ladder and say, if I'm using mathematical induction, then instead of saying I need to get on the bottom of the ladder, what that's analogous to in mathematical induction is saying it's true for n equals 1. So if I can start the process, if it's true at the start, that's one of the things I need. And then the other thing I need to be able to do is to say, well, let's assume it works at some point. So we assume it's true at some value, and we'll call that value k. Then we have to prove it's therefore true for the next value, which would be k plus 1. So that's mathematical induction. Let's do the example. So the first thing I have to do is I have to check that it's true at 1. So step 1, check it holds for n equals 1. And the way I do that is I evaluate the left-hand side, and the left-hand side is the sum from r equals 1 to 1 of 2r minus 1. So adding up all the odd numbers from 1 up to 1. If I add up all the odd numbers from 1 to 1, that's just 1. And the right-hand side, do the same thing. Let's evaluate the right-hand side. Well, I've got n squared, which is 1 squared, which is 1. So it's true for n equals 1. I can get on the ladder. That's usually the easiest part of mathematical induction. The next part is saying, well, let's assume that I'm somewhere on my ladder. Assume I'm at some point on my ladder. So assuming it's true for n equals k. So k is some point on my ladder, and I need to be able to get to the next rung. So if it's true for n equals k, so from r equals 1 to k of 2k, sorry, 2r minus 1 is equal to k squared. And what I'm going to show is that if I assume that, then I can deduce that it's also true for k plus 1. So I'm going to show it's also true for k plus 1. At this point, it's sometimes a good idea just to have a little think what that would look like. In this case, it's pretty simple. If it's true for k plus 1, what I want to show is I want to show that the sum from r equals 1 to k plus 1 of 2r minus 1, so the sum of the odd numbers up to k plus 1 is equal to, instead of k squared, k plus 1 squared. That's what I'm trying to show. Okay, so how can I do that? Well, I'm allowed to start from this rung. I'm assuming that that's true. So how can I get from this line to this line? Well, all I've got to do is add the next odd number. So I'm going to add the next odd number on. The next odd number would be 2 times k plus 1 minus 1. That's the next odd number. So I'm going to add that onto both sides. Add the next odd number to both sides of my equation. Not both sides of that equation, though. That I'm not allowed to assume is true, but both sides of this equation. Starting from there, I'm going to add the next odd number to both sides. And we get, well, obviously, if I'm just, the left-hand side is just adding the odd numbers up. So I get what I want over here. So I've added the next odd number. On the right-hand side, k squared plus 2 brackets k plus 1 minus 1. So I'm going to rearrange that a little bit. Super slowly. And k squared plus 2k plus 1 should look like something we're familiar with because it factorizes the k plus 1 squared. So what I've done is starting from this line that I assumed was true. That was my assumed line. I've proven that the next one is also true. So what that means is, let's say this was the first rung, it would mean I can get to the second. If this was the second rung, it would mean I could get to the third. If this was the third rung, it would mean I could get to the fourth. It doesn't matter which rung I was on. I can always get to the next one. If I pick the 8th odd number, I'd know it's also true for the 9th. So therefore, by mathematical induction, the statement is true. I'm going to do one more example for you. I'm going to do my example from last lesson, the example that the square of an odd number is always one more than a multiple of 8. Square of an odd number is always one more than a multiple of 8. And all I'm going to do is I'm going to firstly show that that's true for n equals 1. And I'm going to show that it's, if it's true for k, then it follows for k plus 1. Before I can do any of that, I just need to be able to state the problem. So the square of an odd number, say 2n minus 1 squared, is one more than a multiple of 8. So I'm going to write this. I'm going to write 8 divides 2n minus 1 squared minus 1. That's what I'm trying to prove. Let's break that down. That's saying 8 goes into, that's what this symbol means if you've not seen it before. It means divides. So 8 divides, or 8 goes into the square of an odd number minus 1. So 1 less than the square of an odd number. So, 2 steps. Firstly, check for n equals 1. Well, n equals 1, so I've got 2 times 1 minus 1 squared minus 1 is equal to 1 squared minus 1 is equal to 0. Does 8 divide by 0? Sorry, does 8 divide 0? 8 goes into 0. Yes, it does. So it's true. For n equals 1. So then we assume for n equals k that eight goes into 2k minus 1 squared minus 1. And I'm going to show that the same is true for k plus 1. So let's do that. For k plus 1, well, what number am I interested for k plus 1? I'm interested in this number. Instead of 2k minus 1, it's 2 k plus 1 minus 1 all squared, and take 1 away from that. So that's the next odd number squared. Simplify out this bracket. I'm going to get 2k plus 2 minus the 1, which is plus 1 squared minus 1. And if I square out that bracket, I get 4k squared plus 4k plus 1 minus 1, obviously, is 0. How does that help? Well, this looks quite a lot like this if I expand this out. So let's have a quick look at what that looks like if I expand it out. Because we know that 8 divides this line here. So what's that expand to? It expands to 4k squared minus 4k plus 1 minus 1. Again, they go to 0. So we know by our assumption that 8 divides 4k squared minus 4k. How are we going to use that over here? Well, I'm just going to separate this out a little bit. I'm going to separate this out into 4k squared minus 4k plus 8k. Hopefully, you can see that these two things are the same. Minus 4k plus 8k makes minus 4k. What's the point of doing that? Well, the point of doing that is that 8 goes into that first thing because of our assumption. That was our assumption from the start. And 8 goes into this because it's being multiplied by 8, so it's in the 8 times table. So that means since 8 goes into 4k squared minus 4k, by assumption, and 8 goes into 8k, by definition, k's got to be a whole number, right? K can't be a decimal. And that means that 8 goes into our original statement. 2k plus 1 minus 1 squared minus 1. So by mathematical induction, this is true. Okay, I'm going to ask you to try one dead simple one yourselves for the lesson, and that's to prove that the sum of the integers from 1 to n is equal to n over 2 times n plus 1. Formula you've seen many times. Triangle numbers. I'd like you to prove that by induction, firstly by checking that it's true when n equals 1, and secondly by checking if it's true at n equals k. Prove it for n equals k plus 1. Best of luck.